Welcome, everybody. Today we are very excited to have Camille Daya present their IJCAI 2022 paper, Multiband VAE, Latent Space Alignment for Knowledge Consolidation and Continual Learning. Camille is a PhD student at the Warsaw University of Technology working on generative model and, more importantly for us, generative continual learning. We are very excited to hear more about this paper, so without further ado, I will turn it over to you, Camille.
Thank you very much, and hello to everyone. I'm very happy to present to you today our paper. As already mentioned, it's called Multiband VAE, our latent space alignment for knowledge consolidation and continual learning. But before I move to the very specific things about our contribution, let me start with a general problem of continual generative learning. I'm pretty sure that the community in this group or possible viewers will know a lot about continual learning, but I want to emphasize a few things about how continual learning differs in terms of generative part. If I speak about continual learning and generative models, what people usually think about, like the first thing that comes in mind is the usage of generative models as a source of rehearsal examples for continual learning. But what I want to emphasize today is that this is not the only thing that we can actually use generative models for. There is really a lot of interesting things going on when we try to train generative models in the continual learning regime. They, of course, suffer from catastrophic forgetting as any other neural networks, and they have many interesting features that I would like to discuss. Let me first start with a very simple scenario. Let's assume that we have a generative model that we want to train on the one task at first. We've recently, for example, let us assume that this task is images of frogs and horses. With recent advances in generative modeling, we should probably be able, especially with the latest diffusion models, for example, we should be able to learn what is the data distribution, and we should be able to ask the model to generate new samples that are very similar to those observed in the original dataset. So we should be able to generate new samples that follows data distribution that we have in our dataset. Now, if we have the same model and we retrain it once more on a new task, which, let's say in our case, are photos of cars and planes now, the model is suffer from the catastrophic forgetting, and we'll observe it not as in a drop of accuracy as we would in standard discriminative manner, but for generative models, we will see that the model cannot anymore generate any new data points from the data distribution that was trained on previously. Usually, when we retrain the model on a new task, what the model will learn is to focus only on the new data distribution. So it will be able to generate new samples such as planes and cars that match data distribution that was retrained on. But even if we train the model that is conditioned on the task ID, for example, it won't be able to create examples from the previously observed data distribution. So there are many methods that are applied to generative models in order to prevent this catastrophic forgetting. And probably the audience of this from this group will already know at least one method that is very common in continual learning, and it's called generative replaying. The simplest possible way of preventing forgetting with generative models is that we can use, of course, some previous data examples that we use for rehearsal. And since we are dealing with generative models that can actually produce samples from the previous data distribution, it's even simpler because we can use the model itself to create for us the previous data examples. So in order to prevent forgetting, we can always retrain the model with a combination of new examples and some previous data generations. However, this approach, of course, it mitigates the catastrophic forgetting, as we may expect, but it's definitely not perfect. One thing that I want to emphasize, one problem that might occur with this kind of processing is that we may suffer from the problem of degradation of previous examples. I want to trying to think about this, what we actually want to achieve while retraining the model in the way how we do it in generative replay. There, in fact, what I want to that there are actually two objectives that we want to train with at the same time. We have a new batch of data, and we want to learn at first how to. The first thing we want to learn is how to encode this new data into the latent space of our generative model. Like, for example, in the case of Variational Autoencoder, we want to train the encoder how to map new data distribution into the latent space it has. And at the same time, we want to, from the same model, from the second part of the model, which is the coder, we want to, we train it to generate new examples from the new data distribution from whatever we have in the latent space already. So if we train the model with generative replay, and we use some past examples that the model already know how to encode, it will learn to encode them into the proper place in the latent space, and probably it will easily learn to decode them, decode any examples that are presented in the latent space into data that is presented to the model at this, right now. So into data examples that are currently available. You can see this leads to this data degradation that I wanted to mention, and you can see the results of this training on the right side of my slide. This is a very simple example when we train the variational autoencoder with generative replay first on images from MNIST that contains only ones, and then we retrain it with the rehearsal examples, and additionally on the new data that comes from the second task that contains only zeros from MNIST. As you can see, model degrades some examples from the previous task. Some of the ones, it degrades them into something that is in between of ones and zeros, because it cannot distinguish those two objectives that it actually has to be trained. So we wanted to ask one question. How can we actually align data from consecutive tasks in the generative model's latent space? And the answer to this question is our method that we call Multiband VAE. And since we know that there exists this problem of two parts of objective that we want to have in Variational Autoencoder, at the same time when we train in continual learning, we propose to split this process into two parts. So that at first we learn data distribution, and then we consolidate latent spaces between we consolidate two latent spaces from the local model that is trained only on the currently available data, and from the global model that already encodes all of the information that the model was trained on previously. So to talk about it in a little bit more details, we split the process in the following parts. At first, we have what we call a local training, which is a training of a variational autoencoder on like separate variational encoder trained from scratch only on the data that is currently available, in order to learn how to encode new data examples into the latent space that is regularized as in normal variational autoencoder. Then we train additional neural network that we call translator that aligns this new data distribution, what we call band, with already encoded previous data distribution into a new latent space where examples are stored independently of their source task. Finally, we retrain the whole thing in order to have as good generations as possible. We start with let me now go through all of those steps and discuss them in more details. First, what we have in our setup is the local training. So the training of the new variational autoencoder only on the data that is currently available. We train it with with the standard variational autoencoder loss, so with the reconstruction and Kullback divergence in order to regularize the latent space. So we train it to, but we are mostly interested in the first part, which is the encoder that is trained to encode original data samples into the latent space that is regularized to follow this one Gaussian distribution. Then we have the second part of our model that we call the translator. And the whole goal of the translator is to map latent spaces from separate VAEs into a single one where examples are stored independently of their source task. So the translator is a simple neural network that takes as an input a point in a latent space from the variational autoencoder. So any point from the latent space that is regularized to be as close as possible to this Gaussian, together with the specific task identity. And the translator does is map this point into the second latent space that we call C, into the region where it fits the best. So this is the goal of the translator. Now let me explain how we actually train it. And we do it with a gradient going from the frozen copy of a global decoder. So we take a model that is already trained on some previous tasks, and we assume that the model is able to generate all of the previously encoded tasks pretty well. So what we want to do is now to train a translator to take new examples and encode them in this kind of region of the latent space Z that fits the best when comparing to all of the examples that the model already was trained on. So in order to do it, we do it with in the following way. We first randomly sample some previous examples. We take some of their latent representations in the original variational autoencoder latent space, so in this latent space lambda. We take new samples encodings that are generated from our local model into this latent space, and we process both of those all of those samples through the translator into this latent space C, and we process those second latent representations through the frozen copy of the global decoder, and we minimize the reconstruction error, and we in order to get the generations from the previous tasks and some generations of the new images. We freeze the global decoder and process the loss through the global decoder and the translator. Since we freeze that global decoder, we only use it to process the gradient to the translator, and we optimize the parameters of the translator way that so that the new encoded examples are stored in the most fitting space in this latent space Z. Those examples, if you think about it, if what we are trying to achieve is that we want to find the spot in the latent space Z that allows us to create the best possible regenerations of the new examples without actually optimizing parameters of the decoder yet. So the new generations probably won't be perfect, but we'll be able to find what are all of the previous examples from the previous tasks already encoded in this latent space. Where are they located so that we can find the best fitting spot for the new task. If the task is totally different than all of the previous tasks, it should probably be located somewhere in the totally different area of the latent space set. While if it shares some similarities between to some previous tasks, it should be located somewhere close to those similar previous tasks. Finally, when we finish with this training of the translator, we optimize both our main networks, so the translator and the global decoder, with the same generative rehearsal, generative replay methods as I discussed previously. So with a combination of new images that are currently available and previous generations generated by the frozen copy of the model. Okay, this is the end of the training, and now let me introduce one more small detail that we propose together with our method. We call this this additional thing controlled forgetting mechanism, and we introduce it in order to facilitate the knowledge consolidation in our method. If you think about it for a moment, whenever we train generative model in continual learning setup, it actually all of the samples that are rehearsed and rehearsed once more suffer from the accumulation of the error. If we regenerate them once and then we try to regenerate them second time and third time and so on, we can see that they degrade with time a little bit. So because of that, we think that what we propose is that to take this into account and try not to stay too much connected to those examples that we know that might not be so perfect anymore. And whenever we have something that can replace it, we want to actually make use of it. So in particular, what we propose is that whenever we train the model with already pre-trained translator, wherever we retrain the global model in the final generative replay method, we have some sample. We have all of new data embeddings already generated. So we know where those new data examples are stored in the latent space Z. And now whenever we sample a sample for rehearsal from the previous, any of the previous tasks, we first measure how close it is to the closest possible example from the new data set from the new task. And if we consider that those two examples are actually super close to each other, we propose to forget this rehearsal example that was present, the model generated as a rehearsal example, and we propose to substitute it with the new example so that we make sure that whatever is starting here in this latent representation, it won't be anymore the previous generation, but it will be totally substituted by the new example that is super similar. This allows us to make sure that our model is that the plasticity of the model is high, and we can easily adapt to new data sets, even if they are partially similar. Let me now move to this experiment section to show you how our method works in practice. But before I move to those beautiful tables with state of the art and so on, I want to talk about one important thing when it comes to generative continual learning. I already mentioned that our method uses task identity a little bit, and I want to emphasize how that actually this is not a big flaw of our method or any generative continual learning method. Well, task identity in discriminative models simplifies the problem of continual learning. Whenever we have a method that uses task identity in order to properly assess what class the model is, what class is of the sample that we have, whenever we have this kind of situation, it actually the problem is a little bit more simpler, because the task identity already can allow us to get rid of a lot of examples, a lot of classes that the model should not focus on. In generative continual learning, it's actually not that simple. In the final outcome, what we actually want to have in generative continual learning is a generative model that is able to generate samples from the sum of data distributions that were presented to it in a consecutive way. So what we want at the end is to be able to generate all of the any examples from all of the distributions that we had. If we use the task identity in the generative model, in the continuation generative model can actually easily sample it in the same way as we sample random noise in order to generate new examples. So in fact, we end up in with the same model without any drawbacks. It still can generate all of the examples from all of the previous data distributions. We only have to sample the task ID in the same way as we sample the random noise. However, what I want to emphasize is that comparing generative continual learning to the standard discriminative one, there is one significant difference, that the class incremental scenario that is considered the most problematic or one of the toughest ones for discriminative models is actually very simple for generative model, considering the fact that we can use task identity. What we want the model to do in the class incremental scenario is to learn a totally disjoint data distributions per task. If we have, for example, different class in different task, the data distribution that the model has to learn is different per task. So it's easy for the model to actually learn those disjoint data distributions, taking into account just the task identity. So because of that, we see this simplification that is present in the general continual learning when it comes to generative continual learning part, that type of the problem, and we propose a new continual learning scenario that is designed especially for generative models. So we draw inspiration from federated learning, and we propose this novel scenario that we call knowledge consolidation one, where we want to make sure that the data distribution that comes to the model from between tasks is not disjoint. So we don't want the situation that the upper bound of our solution is actually a separate model trained on all of the disjoint tasks. In order to make sure of it, we propose a scenario where we refer to the Dirichlet distribution, and we propose that for each task we'll allow to draw classes according to the Dirichlet distribution. So you can see some examples in here. All of those different colors are examples from one given class. But in the standard class incremental scenario, every task comes with two totally different classes. In our knowledge consolidation one, we propose to split every class randomly into different portions of a different size between different classes. For example, with Dirichlet, with the alpha equals to 1 parameter, we have a situation where the majority of where tasks are generated in the way that majority comes from one class, while the rest of the 1 or 2, let's say, the rest is split into different tasks. So, for example, if you consider the yellow class here, we have it divided into 4 different tasks, and if we train the model on this kind of scenario, it actually has to learn from many different tasks in order to have the best possible performance. If we go a bit further with the changing the parameters of the Dirichlet distribution, we will end up in a situation where classes are almost evenly distributed between tasks. So this scenario allows us to change how much we want to focus on this, how much we want to change between making it easier or harder for the model. Okay, so let me now move to the results of our methods, and let me start with a very simple toy example of that will present how our model actually works in practice. So in here, I want to compare our solution with the standard generative replay. I want to once more emphasize that the generative replay in both generative replay and our method uses the task index in order to generate new samples. And I want to show you how those two methods work differently in two scenarios, where we have the standard class incremental scenario with disjoint data distributions and our proposed partially Dirichlet-based scenario where between classes we have between tasks we have partially same classes. So both models are based on variational encoder, and they start with the latent distribution that you can see in here. That is actually the same because it's the same variational encoder model trained on the same data. But then we train the model with a second task that is in the class incremental scenario with the different distribution. This time, this is MNIST dataset, but only classes, only examples that are the class 0. And what you can see in here is what I already showed previously, that because of these two objectives that we have with generative replay, model suffers from the problem of the previous data degradation. Our model, thanks to this fine-tuning of the translator first, it is able to instantly separate those two distributions because they do not match. There is no, it doesn't help if we place those examples together close to each other when it comes to reconstruct them. So model instantly separate them and doesn't suffer from the degradation. However, if we now retrain the model, those models on the third task, where we have partially similar classes. So in this case, we have ones that were already present there in the first task, and twos that are like from the different distribution. We can notice a few more observations. So we still can see this previous data degradation that was already there in the previous task. So model will keep it in mind. Will keep it in the latent space forever. And will degrade even further. But what we also see in this generative replay is that it doesn't align so good. So when it comes to new data examples, so for example, those twos in here are located very close to the region, red region that actually consists ones probably. On the other hand, when you take a look into the latent space of our model, you can see that zeros are still separated totally from the rest of the classes. While in here you can see a very good alignment between different classes coming from different tasks. So we can see that ones coming from that are generated as a response for task index 1 are very close to those ones that are generated as a response of task 3. So they are very close to each other. While the twos are a bit further away. So once more to emphasize, what I wanted to say is that our model is able to prevent catastrophic forgetting when we have a situation that when the new data distribution is totally different than the other one, while at the same time we are able to properly align data representations from partially similar tasks. For example, where we have partially overlapping classes. This allows us to continually improve with time, and we can see it with the forward and backward transfer that I will show in a moment. First, I want to show to you that our whole evaluation, where we evaluated the many different generative continual learning methods on different scenarios, including both standard class incremental and our scenario with Dirichlet approach. As you can see, for example, here in the OmniCode dataset, we have exactly the same number of tasks, so 20 in here and here, and you can see that most, is not all of the related works have lower performance when we actually try to retrain it with partially similar data. It's easier for most of the methods to actually be trained to be trained on totally different disjoint data distributions. So they really suffer from this problem of not being able to consolidate knowledge between tasks. What I wanted to emphasize is that with our method, we are able to observe both forward and backward knowledge transfer, which is very important in terms of, which actually shows us that the model can accumulate this knowledge. So we can see forward knowledge transfer because, for example, as presented in here on the ContinualAI dataset, can observe lower FID scores, so better performance from task to task. While at the same time, we see even backward knowledge transfer, which means that when we retrain the model, the partially similar data, it can improve when generating samples even from the past tasks. So this is thanks to this. So we can see, for example, in here that we start at the beginning, we have of the third task, we have the performance on the third task that is with this 80 FID score. And when we retrain the model for 2 more tasks, it actually goes down. So the model generate those examples even better than it did previously. What I want to show at the end is once more the performance on ContinualAI dataset, and what I wanted to show that is that our method is able to really to both prevent this catastrophic forgetting when we have class incrementals set up. It has much better performance than, for example, separate models or generative replay. But when we change the scenario, we can see that the more aligned are the tasks. So the simpler they are, the better is actually the performance of our method. And if we have the situation where the data is aligned almost perfectly, so in each task we have more or less all of the classes, we almost reach already the performance of the upper bound, so the model trained with the full access to the data. So even though it's trained continuously in the continual learning setup, we reach almost the performance of the model trained on with the full access to data. Finally, since I'm talking about generative modeling, I wanted to show a few examples of how the generations looks like. And here are some samples from the ContinualAI dataset and fashionist to MNIST datasets. So it means that first train on the fashionist for 5 tasks, and then we move to the MNIST dataset. And what I wanted to show you in here is that how the model actually learns to align those two different distributions. So in each column in here, the models are actually generated from the same random noise, but with different task conditioning. And what you can see in here, because of that, it's how model is able to align some certain features of the from the datasets, even from like totally different datasets. So for example, on the right, you can see that those very dark clouds are properly aligned with digits that are in bold, which is some feature that is common for those two datasets. And on the other hand, in here you can see some light clouds that are aligned with some very light style of writing. So this is all thanks to this consolidation of knowledge, even from totally different datasets. Okay, so as a conclusion, we propose a Multiband VAE, a method for continual learning of generative models. We additionally observed that correctly applied class incremental scenario, although it's very tough for discriminative models, actually simplifies training for generative models. And we propose a novel knowledge consolidation scenario that is designed especially for continual generative learning. We present that our approach is able to prevent forgetting while still accumulating knowledge from consecutive continual learning tasks. Okay, this is all from my side. I wanted just to emphasize that this is not my work. It's in collaboration with my great collaborators under this greater project where we try to look on generative, on continual learning from the generative view perspective. Happy to take now questions if there are any.
Great. Thank you so much, Camille. And we actually do have some questions. I'm going to start with one from YouTube Live. And you may have touched on this in slide 22, but I was not sure if those examples were from a combined task or not. I guess they were. So I'll only just ask the question, and I think you may have answered it here, but how does the model perform when you have sufficiently distinct tasks? So like if task 0 was to generate from faces, and then task 1 was to generate from automobiles, and I think maybe this is what you did right here with fashion
Yeah,
MNIST to MNIST, which, but
like,
I'll let you
exactly.
re-hammer that conclusion, I guess.
Yeah, exactly. This is what I wanted to present with this joint data sets, that even when it's like totally different, the model simply separates those two distributions, and but still there are some features that are similar. So it can align those features, and it still can generate those features properly.
I'll ask a question that goes on the opposite of that. So you have this very intuitive, controlled forgetting mechanism. My question is, could this? So I see how this could help, for example, in your new mixed task things where you control them with the Dirichlet distribution, and it makes sense that you'd have some controlled forgetting. I think that's a very practical aspect, but on the flip side, could this hurt you when you have very similar tasks? Like, and one side of that could be like slightly like in the classic incremental experiments. Could this end up, making some of your tasks more difficult to separate if you have some of this maybe incorrect controlled forgetting? Yeah, that's my question.
Mm-hmm. Yeah, so I can see when it might be problematic, but what we want to apply this control forgetting already on the pre-trained model, pre-trained translator. So we already have the situation that we know that the new data distribution is located somewhere in the latent space with respect to all of the previous data distributions. So if it's super similar, it will be super close. But if it's different, then it shouldn't be in the same place. If we have very similar tasks, if they are identical, there is no problem. But if they are very similar but still like a little bit different, then that the model should be able to learn it. I hope, I think. That the distinguishing between those two tasks, because this will be crucial for the generation of when it comes to reconstruction error, because if there is this different, there should be placed somewhere else. But anyway, I can imagine the situation that we, of course, override some samples from the from the very similar samples. But I still don't think this is a very big problem, because for rehearsal, what we actually do is we sample from the latent distribution. So the probability of sampling from the place where the original example from the previous task was actually encoded, it's 0. So we only replace like interpolations of many previous examples, probably with new samples. So it should be usually better. At least in our experiments, it always was better.
Okay, yeah, that makes sense. Last call for questions. I have one more. This is a little, extending future outlook, but I'm wondering if this mechanism could be combined to also learn a global encoder model as well, and perhaps applying some of the foundations of your approach to not just learn generative tasks, but perhaps to even help discriminative tasks. Is that anything that you've considered or could comment on?
Exactly. This is something we are working on right now together with my 2 students. So we actually have a very good progress in this. So we have like this kind of global, let's say, encoder task or feature extractor that is doing the same thing as the encoder, and we are applying the classification problem. So that we can
Don't spoil
combine
all
those
of your
two.
work.
I won't. I hope you'll see the results pretty soon. So.
Great. I'll look forward to it. If there are no more questions, I think we could wrap up at this time. So thank you so much, everyone joining today, especially those who are working hard towards the CVPR deadline. We appreciate you following along on YouTube Live, or perhaps watching this at a later time. Thank you, Camille, for this wonderful presentation and work. Everyone, please join us next week for the next installment of this series. Please note there will be a time change Our presenter is located in South Korea and for some strange reason did not want to present in the middle of the night. So that will be announced with our regular announcements, a time change for next week. So thank you everyone for joining and have a great rest of the week.